Oh, can you hear me?
Yeah, we can hear you. Yeah, perfectly.
Okay.
Okay. Uh, good evening, everyone. Firstly, I would like to thank the organizer for the invitation to give a presentation in this very good international workshop on high-energy physics. The topic of my presentation is about the fully charmed tetraquark states observed recently by the LHCb collaboration, the X6900 and some other states. And also I will discuss their strong decays into the di-charmonia. My presentation is based on these two papers. The first one is before the observation of the experiment, and the second one is after the experiment. So this work is in collaboration with these people. Firstly, I will give a introduction of the background of the exotic hadron state, including the XYZ state, the pentaquark state, and also the fully charmed tetraquark state. And then I will introduce the theoretical method we use. Is the moment sum rules for the calculation of the fully charmed and fully bottom tetraquarks, and then discuss the decay properties of this four heavy tetraquarks. Sorry, to enter the full screen. Okay. We know the quark model is established by Gilman and Zwick.
Sorry, it's not. Ah, yeah.
Sorry.
Sorry, all is fine now. Yeah. Please continue. Go on.
You can see the slide. Can you see the slide?
Yeah, we can see it perfectly. Yeah. That's right. That's okay. Sorry.
Okay. So, the quark model is established by Gilman and Zwick in 1960s to clarify the hadrons in quark model. The meson is composed of pair of quark and antiquark, and baryon is composed of three quarks. However, in the fundamental theory of strong interaction, the quantum thermodynamics, the hadron structure can be more complicated than in quark model. It means the number of the quarks can not equal to 2 or 3. This complicated hadrons outside the naive quark model, we usually call them the exotic hadron states. Actually, in history, we have a very long time in the experiment for searching for these exotic hadrons. Even before the birth of the quark model, like the deuteron and the lambda 1405. The deuteron is a candidate, is a very good candidate of the dibaryons. And also we have some other candidates like the H state, the D star 2380, and also for some other candidate of the exotic, we have a hybrid, global, tetraquark, pentaquarks in the light hadron sectors. Before the year of 2000, the experiment search for the exotic hadron are mainly focused on the light hadrons. However, the real breakthrough of this exotic happen in the heavy hadron sectors. Firstly, in 2003, the Barrow collaboration find the X3872, the first XYZ state.
Sorry, something happened.
I can hear you. I cannot hear the speaker.
Yeah, I cannot see him also on the list of participants. I can trying to find him, but I failed. It seems that he disconnected. Probably he had some problems with internet connection or something like this. Let us wait probably for some time. Probably he will able to handle it. So something happened because first I yeah, sorry.
Hello?
Yeah. Hello, can you hear us, right?
Hear me?
Yeah, now we can hear you.
Okay, sorry for the problem. I will
Yeah, it's okay, no problem. So I mean, you can share your slides once again.
Yeah. Okay, I just
Yeah.
continue the talk.
Yeah, sure.
Yeah. Okay. In last year, the LHCb combined their run 2 data and they find this peak.
Yeah, but maybe you can share your slides.
Oh, share my slide. Share screen.
Yeah, I mean, share your screen, of course. Yeah, and show your slides. Yeah. Okay, great, perfect.
Yeah. And they find this this narrow peak can be split into 2 peaks, and in addition, they find another narrow peak named PC 4312, and all of these three states just below the threshold of the sigma C D star and the sigma C D threshold. So this observation is extremely inspired the theoretical interpretation for this 3-state is the hadron molecule interpretations. And in this year, just one month ago, the LHCb collaboration also find another PC state contain a strange quark. They find this state, this PCS 4459 in the gypside lambda final state. The main mass is around 4459, and the width is also very narrow. So it seems that in this year the LHCb collaboration give more and more important contribution to the exotic hadrons. However, before LHCb, there are also many other experiments like the barrel collaboration, Baba and Best3, CDF, Clio, D0 also give some give important contribution in this field. They find more than 30 XYZ states in the B metal decay, the E plus minor annihilation process, and the double charmonium production process, and the gamma fusion process, and also the decay of the Y42 60s. Most of these charmonium-like states were actually discovered above the open charm threshold. In this figure, we can see this XYZ state in this color and this color. They all of them are above this open charm threshold, and we can see their masses and the decay widths are very different from the prediction of the potential model for the pure CC bar charmonium-like charmonium states, especially for some ZC states, because the ZC state is charged, and their final state contain also a CC bar pair. So they should contain at least 4 quarks. So to explain this XYZ state, especially for the ZC state, the tetraquark and the hadron molecule configuration were extensively used. In the ZC state, we have a pair of CC bar and another pair of light quark, like a UD bar. So the question is, if this ZC state exists, then what happened to replace the light quark to be a heavy quark? Like we replace this system to be a 3 heavy quark system, or even the 4 heavy quark systems. So what happened for these systems? Actually, this kind of system, a tetraquark system in QCD, has a very good QED F-log. In QED, we have a similar system is composed of a pair of E plus minor pair. This is called the molecular postronium. This is the PS2 bound state. This PS2 bound state is actually already discovered in 2007. So this system in QED can form a bound state. Then we can imagine in the similar tetraquark system in QCD. Actually, this kind of 4 heavy tetraquark states has some advantage in QCD. Firstly, they are far away from the mass range of the observed conventional QQ bar hadron, like the charmonium and the bothmonium hadrons, and also they far away from the charmonium-like states, like the XYZ states. So this 4 heavy tetraquarks can be clearly distinguished from the experiment, from the normal state and the XYZ state. And secondly, because they contain only the heavy quarks, so the light meson, like the pion, the rho, omega and sigma, cannot be exchanged between 2 charmonium and 2 bothmonium. So the binding force between these 2 charmonium and bothmonium can only from the short range gluon exchange. Then this 4 heavy tetraquark can be a very good system to distinguish the configuration between the compact tetraquark and the loosely bound hadron molecule. In the experiment, in this year, just several months ago, the LHCb report several resonance structures in the di-gypside mass spectrum. They find 2 structures here. The lower one has a very broad range from 6.2 GeV to 6.8 GeV, and another one is a much narrower one. It's mass around the 6.9 GeV, and they gave the parameters of the mass and decay width based on 2 models. The first model is based on a no interference model. Their mass is about 6.9 GeV and decay width about 80 mass. And the second model is it's a simple model with the interference. So the mass is a little bit lower, and the decay width is much broader. So it is interesting. It is interesting for us is this experimental observation is are consistent with our theoretical work in 2017. published in PLB. So I will introduce this work based on the Q3 sum rules. Okay. The Q3 sum rule is start from the 2-point correlation function of the is induced by the inflating current, the Gx, and the Gx has the definite constant numbers like the JPC equal to 0 plus plus. So firstly, we need to compose the tetraquark in the plating current contain 4 heavy quarks with the definite constant numbers. I give the 5 in plating current with these constant numbers as an example, and then we can calculate the two-point correlation function as the quark and gluon level by the operator product expansion method to calculate this Feynman diagram, including the perturbative term and the non-perturbative term. Actually, in this fully heavy tetraquark system, the non-perturbative term is very simple. They contain only the gluon condensate and the trigluon condensate. But because the trigluon condensate is much smaller than the gluon condensate, so in our calculation we only consider the gluon condensate. And as the hadron level, we already described the correlation function by the dispersion relation. Then we do some the method of the to define this moment contained at the point of the Q0, and then we can pick out the bound state contribution from this moment, and this data contain the higher state and the continuum contributions. So then we can establish the sum rule about the hadron parameters by establishing by equal to the correlation function between two sides, the hadron side and the quark side and the quark gluon side. So we can extract the hadron mass as a function of the n and Q0. So there are two important parameters in our Q3 sum rules. Is parameter n and parameter Kc. Kc is just a definition of the Q0. So we have some criteria to choose a very good parameter region to make sure the Q3 sum rule can be stable, and to find this parameter region, and to find some working regions of this parameter and of this parameters. Then, as an example, I show example of the 0 minus plus channel, and to give their math curves, and we can find these math curves have the plateaus at some point, so we can give the math prediction at these plateaus. And for this channel, the math prediction is about the 6.8 GeV. And this table give a math prediction for the four charm tetraquark system and 4 bottom tetraquark systems. And we focus on this fully charm tetraquarks. We can find this in this math spectra. The blue one is the has constant number 0 plus plus and 2 plus plus. Their mass is about 6.4 to 6.6 GeV, and this mass range can be consistent with the LHCb's observation with the broad structure around 6.2 to 6.8 GeV. And also the red one, the red channel for the 0 minus plus and 1 minus plus, their mass is about 6.8 to 6.9 9 GeV, and this mass is agree with the mass of the X6900. So our calculation suggests this lower broad structure to be S-wave four-charm tetraquarks with the constant number 0 plus plus and 2 plus plus. And we suggest the X6900 to be a P-wave four-charm tetraquarks with the constant number 0 minus plus and or 1 minus plus. We can also find the positive parity tetraquarks. Their mass is much lower than the mass for the negative parity ones. That is because the positive parity channels are the S-wave tetraquarks, and the negative ones are P-wave tetraquarks. Okay, in this plot, we find the prediction for the fully charm tetraquarks almost lie above the di-gypsy and the di-eta-C threshold, and the fully bottom tetraquarks lie below the di-epsilon and the di-eta-B threshold. For the decay behavior of the four-charm tetraquarks, because their mass is lie above the di-eta-C and the di-gypsy threshold, so they can decay to the di-charmonium final state via the rearrangement however, because the mass splitting is very small, so the phase space may be small, and some other decay channel like the two doubly heavy baryon states can be forbidden because the mass is smaller than the pair of doubly charm baryons, and also for this kind of decay is also spread because there are two light quark pair creation, and also a pair of heavy quark annihilation. So the possible decay, strong decay, can be this kind of decay directly to the double charmonium, and also they can decay by a pair of CC bar annihilation and also a creation of the light quark pair to be to the final state for the DD bar or D star bar. So after the observation of the LHCb, we consider the first decay process to the di-charmonium, and we consider all these quantum number channels for including the di-gypsy final state. We can find the di-gypsy final state can only appear in the 0 plus plus channel, and the 0 minus plus channel in the P wave, and also the 1 minus plus in the P wave, and 0 plus plus is in the S wave. So we calculate this relative branching ratios through the Fierz rearrangement by considering all of these di-charmonium final state like the gypsy, eta-C, and gypsy HC, eta-C Chi-C0, and eta-C Chi-C1, and so on. And we calculate their relative branching ratio based on the gypsy channel. And we find we confirmed the conclusion in the previous paper that the broad structure around 6.2 to 6.8 can be explained as a S-wave fully charmed tetraquark with the constant number 0++ or 2++. And the narrow one, the X6900, can be a P-wave tetraquark with the constant number 0- or 1-. And we also propose to confirm them in the di-eta C, just like HC, eta C, Ca0, and eta C, Ca1 channels, because we can find if the for example, if the X6900 can be a 0- or 1-, but the different decay channel has a different the relative branching ratios for these two constant numbers. So if we can confirm these two decay channels, like the di-eta C. The di-eta C only appear in the 1- channel, but do not appear in the 0- channel. So if we confirm this X6900 in the di-eta C channel in the experiment, we can determine the constant number of this state. Okay, skip to the summary. The LHCb collaboration had observed two resonance structures in the just pair mass spectrum. They find X6900 and a much more broad structure around 6.2 to 6.8 GeV. And before this observation, we have calculated the mass spectra for the 4-charm and the 4-bottom tetraquark states. And then we also study the strong decays of this possible fully charmed tetraquarks into the di-charmonium final state, and we calculate their relative branching ratio through the Fierz rearrangement. And our results suggest that the broad structure can be interpreted as the S-wave 4-charm tetraquark state with the constant number 0++ and or 2++, and the narrow one can be a P-wave one with the 0- or 1-. And we propose to confirm them in the different di-charmonium channels and to determine their constant numbers. Okay, thank you.
Окей, ой, а что-то я исчез. Okay, thank you for very instructive talk. Just now I'm waiting for questions to report.
Yeah, there are two hands raised. So,
Okay.
Nuzar and Vladimir. So Nuzar, you were first.
Okay. These exotic charmonium states are as non-relativistic as usual charmonium. So it seems potential model might be Quark. Thing is that usual Cornell potential needs some crucial modifications. You told that we cannot improve situation by light meson exchange between the charmonium-like constituents. So one way that remains in non-relativistic approach is to modify Cornell potential in the way that we will have the bound states like that exotic.
Because it's a different from the XYZ state, like the D and the D bar system, because their interaction between two charmonium cannot be you cannot obtain the potential by the like the one meson exchange model, you need to consider I think the gluon exchange potentials to obtain the potentials. So I think they will be very different between the XYZ state.
Okay.
I have a
Next question.
well-motivated potential from gluon exchange, non-perturbative gluon exchange. Thank you.
Okay. Okay. Just now I said that we have a break on 1 hour.
Yeah, but
Can I ask a question also?
yeah, possibly Vladimir, another question.
Okay,
Yeah,
I have a question. The following: do I understand correctly that your results show that all bottom tetraquarks are below the threshold for decays to 2 epsilon? Yes.
Oh, you mean the four bottom tetraquarks?
Yes, for bottom. Then
yeah.
how can you explain the data from LHCb and CMS collaboration that there are no narrow structures in the epsilon pair spectrum? In the
Yeah. That is a very interesting question. Actually, I also sent an email to the discussion leader. Just this question as a list in the discussion session to discuss why the LHCb and the CMS have very different results to find this 4B state. I think
now they have similar results. They do not see. There was some preliminary results which were not published by CMS that they saw some possible signal, but now the last published results, they do not see any structures in this double epsilon production.
Okay, thank you for the remind.
Okay, and I also have another question. Can you show me the diagram where you calculate the decays of this tetraquarks?
The diagram. This diagram?
Yeah. Well, why do you not consider rearrangement of the? I think that it will be the main decay channel.
Yeah. You're right.
Because there are no rearrangement diagrams shown here.
Yes, you're right.
The diagrams that you show are significantly more suppressed than the rearrangement diagram.
That's true. Yeah.
Here,
I just use the wrong diagram in this.
I think that this diagram will be the most important one. And
yes.
The phase space is rather large. This decays should be rather rapid, and you can explain by such diagram only the broad structures, at least for the ground states, for the S wave states. For excited states, of course, you need just to go the suppression due to this excitation, this barrier, centrifugal barrier. Then it's okay. Maybe this can be a narrow state, but the ground state with such large phase space should be broad in any case. I think it's confirmed on your transparencies, but if you calculate the diagrams which are only shown here on your transparencies, then you will get a very narrow state.
Yes, you're right. Thank you for the comment. I just need to change this. I use the wrong diagram here.
Okay.
Yeah.
Thank you.
Thank you.
Okay, thank you very much for all speakers. Just now we have a 1 hour break.
Yeah. Okay, so thanks a lot, Anatoly, for chairing this session.